So in the last lectures, I talked about various aspects of quantum computation using the technology of NMR. It was a ready-made situation in terms of high precision instruments already available. You just had to redesign your ideas about what to do with them, and it was a good demonstration for many concepts on a reasonable size processor going up to about 10 qubits. The NMR technology has since been extended to other type of quantum system manipulations. And I will give you a brief story of some of those topics. And well, it's not necessarily in direction of computation, but a lot of it is actually in the direction of sensing and measurements. So these are all applications of magnetic resonance, and they have been very useful in different fields. One of the first thing which was already there actually by the time this quantum implementation came along, it goes under the name of two-dimensional NMR. And what the two-dimensional structure corresponds to is two specific directions, or more correctly parameters, time, or you can call it a frequency, and so it is not a direction in space but direction in time variables, and they provide more structural information than what I discussed in the previous lecture, which can be labeled as a one-dimensional NMR methods, because there was only one time parameter which you converted to frequency and observed various kind of signals in that particular context. So because there are two parameters, what you actually measure is certain correlations between those two parameters, and that goes under this acronym which stands for correlation spectroscopy. And there are various versions of this COSY depending on the arrangement. Some extra letters are added to the acronym either before or after. So what is done is you have an initial state, so it is most of the time just a thermal state in NMR Boltzmann distribution, and you apply a radio frequency pulse. This is through that coil and the XY magnetic field, and it will excite some of them. The initial state within the Z basis, it will do something. Afterwards, you let the system evolve for a certain time. So and that is according to the natural Hamiltonian of the system, which is dictated by the 1 qubit magnetic field as well as the 2 qubit interactions, whatever they are in the particular molecule. And after that, you can apply another RF pulse, same type as the initial excitation, which will mix various states. Because of the 2 qubit coupling and this evolution, certain correlations got created. And then when you again apply an RF pulse, it mixes them up. Again, this coupling was in the Z direction and this was going to be in the XY plane. And immediately after applying the second RF pulse, then measure the free induction decay. This is the same procedure which is used in one-dimensional NMR. The system is some mixture of excited states and it decays back towards the ground state in the Z basis. And this signal of this decay is picked up by the same RF coil through what is electromagnetic induction. Okay. So now you can do this experiment as a function of this free evolution which was sandwiched between the two RF pulses. So perform several experiments varying the this system evolution time, this particular step. And then you have two time parameters. One of them is this system evolution, and the other one is the usual free induction decay, which picks up the signal, and you can then plot the signal as a function of both the times. That is what is responsive for the label of two-dimensional NMR. Or you can take the two time parameters, do a Fourier transform, and plot it as a function of frequency. Both are quite all right. So in that two-dimensional analysis, you can observe various features. One of them is the diagonal part gives the same information as the one-dimensional NMR. Diagonal part means that the frequency which you plot, one from the free induction decay and another for the specific time, you keep them the same, and then there is nothing more which you can get from it. Both the frequencies are match, and the results are identical to what you can extract for one dimension NMR, but there are off diagonal terms also. And what do they give? They are going to give correlations. What are the correlations between? And they are between the spins which are connected by the chemical shifts. You have slightly different frequencies of the two, that is the meaning of the off diagonal part. But as I have described, the frequencies of all the spins is not exactly identical, depend on who are the neighbors of what, and that is given by this particular chemical shifts. And then you have a two-dimensional plot. You can remove the global frequency, but you have cross terms between spins which are shifted by this chemical environment, and by varying the time of this evolution, you can see how the correlation is changing between these two neighboring atoms related by chemical shift. If they are not neighboring, then nothing is going to get transferred, because every interaction is a two-spin interaction. If they are far away, that will not produce any signal. But if they are connected by some atom, some correlation will be transferred, and that will be picked up in the chemical shift signal. Okay. So this gives a it's a signal which is quantum. So in the application of the structural information, this is very important. You can measure the off-diagonal peak, and the size of that particular peak will tell you how strongly those two spins are coupled, and that basically gives a part of structural information that just they are nearby, they will have a strong connection, and the frequencies will be shifted, and by varying this evolution time, you will be able to pick out the corresponding signal. So it's essentially the question of coherence transfer, because all these things takes place well within the stability of the NMR system overall, which is of the order of several seconds. So this is how the whole system was already in place in biology and chemistry, and actually it's very useful to study structure of molecules, because you are getting much more information about the neighbors in a molecule compared to what you can get from one-dimensional NMR. And the question is to now reinterpret this in our quantum computation language. Okay. So what this procedure does, it allows you to do this coherence transfer between some neighboring spins. What is its interpretation in the quantum information theory? Well, it is a type of correlations, and if you have the parameters right, that correlation generates entanglement. Okay. So and this is the way it has been used in a quantum information processing. You can create entangled states. The simplest one are of course the Bell states. If you just look at coherence transfer between two spins, not a large molecule, but you can generate Bell states in a clever manner, and then you can do various things which are possible using Bell states, or people have done more complicated correlations like G at Z states, which have three spins coupled together in a particular manner, and you can generate this kind of new correlated quantum states, and after that you can, well, use them as resource in doing some computation. It's not the computation in terms of running an algorithm, but it's computation in terms of generating entangled states, which can have specific uses. Okay. So this is the story of a two-dimensional NMR, and it has a historical connection with Anil Kumar also. You can read his Wikipedia page. He was actually the first person to do pioneering experiments on this particular scenario, and that was when he was a postdoc in Switzerland, and they did lots of different things, and they got immediate applications in studying chemistry as well as biology in terms of structures, information, and Anil Kumar was basically involved in setting up lots of these techniques. And one of his papers is quite famous. It is written with two famous scientists. Anil Kumar is the first author, and both his collaborators got Nobel Prizes. So they were, of course, professors. Anil Kumar was a postdoc, and both the collaborators got Nobel Prizes in chemistry for developing NMR techniques of various types, not just this particular thing, and they got Nobel Prizes in different years. So they had done other work as well, and this work of Anil Kumar actually is cited in the Nobel citations, and that this is the pioneering work which was leading to this particular subject. So yeah, this is a connection with what Anil Kumar did here, and of course he knew all these techniques, and he was creating all these kind of entangled states and doing various NMR experiments together with them. Again, these things was probably done before anybody else implemented it in NMR situations at some other place. So that is a little bit of history, but now I can go to another application of magnetic resonance, and that is also now quite popular for mostly applications in quantum sensing. And these are the objects are called nitrogen vacancy center. So what is it in terms of its structure? So it's nitrogen impurity in diamond lattice, which is adjacent to vacancy. So what it needs is two things. A diamond lattice can have many different kind of defects, and both of these are defects. Vacancy is just a removal of one of the carbon atoms, and nitrogen defect is a substitution. A carbon atom is replaced by a nitrogen. And what you need is both these things have to be next to each other. So it won't happen kind of automatically. You have to arrange for it, and in some situations or some fraction of the atoms you will find this particular configuration. If they are far away from each other, those things are of no use and you don't worry about them. Now what happens is, chemically nitrogen has one more electron than carbon. So various bonds in the diamond lattice will take up all the electrons which are in the valence band of the nitrogen, but one of them is a leftover. And that leftover electron goes and sits inside the vacancy. That becomes the target. So the extra electron and that is a spin half object which you can manipulate with magnetic field. Of course, this is an electron, so the magnetic moment compared to a nucleus is 1,000 times larger. Okay, and so correspondingly, its energy levels are also larger in magnitude. So they are not going to be in the radio frequency range, which is where NMR is used most of the time, but these energy levels are in the optical region, much higher in terms of the frequency. And the advantage of this is that you can see them. It's something which you can manipulate using lasers, and when the excited state decays, whatever light comes out, you are able to see them directly. So now what has been figured out, of course, just having the energy levels is not enough. You need them to be long-lived so that before it decays, you can do some quantum manipulations with it. And there are the so-called metastable states. And because now this is all in a crystalline geometry, you have to study the so-called point group or the neighboring structure of that particular defect to find out what the energy levels are going to be. And they have two labels. One of them is called A and another called is E. And this 3 refers to that they are spin triplet states. Okay. This is what shows up by all the internal dynamics, whatever is present in the diamond. So these are fairly stable. Well, how stable? Again, they live for of the order of seconds. No, it's actually, yeah, smaller. These are numbers which you have to look up, but so what can be done within this time scales is you know the frequencies, and you can make a laser which is in resonance with it, and you can pump those particular transitions, and these are short pulses of lasers, and then you see that it goes to the excited states and it decays. And you can observe the particular decay. That's where the numbers of these lifetimes, etc., come from. So what is the importance of this observation of decay by laser pumping? And that is the point which is related to the sensing, that the frequency is highly sensitive to all kind of external parameter. It can be magnetic field, electric field, it can be temperature, it can be even a mechanical distortion like strain. And by measuring these shifts in the frequency, you make a sensor for all this external environment, and that is a very useful feature to have. And people are developing these kind of sensors for, well, detecting various external features to high sensitivity. And that is a application, nothing related to computation for the time being. But then people have thought of, well, how you can take advantage of, again, this physical system to make something relevant to quantum computation or information. So that some things have been tried, and one of the interesting possibility is that you can have what is a carbon part of the diamond lattice, but which is this isotope 13. And then this has its own spin, but it's a nuclear spin, while this thing is an electron spin. But both of them are magnetic dipoles in some sense, so they can get coupled. And what is the interesting feature of this is that, as we saw for the NMR technology, the nuclear spins are much longer lived than the electron spins. Okay, they have all the usual shielding available from a diamagnetic material. So you can do some things with the electron spin in terms of transitions, but this long-lived neighbor, if it is around, it can act as a memory where you can keep the information protected for some time before you can do something more with the electron. So this is something which people have tried out, that yes, I have some qubit information in the electron spin. I will store it for some time in this carbon 13 nucleus, and after a little gap, I will pull it out again and see whether the initial information is preserved. Okay. It's a simple step, not a complicated thing, but trying to make something like quantum memory is a non-trivial task. It was not there in the usual algorithmic picture where you just start at one end and go all the way till the other. There was no place to store the data. So this is something which people have tried, and it works. Of course, the system is small, 1 qubit for the electron and 1 qubit for the carbon-13, and that is well, a demonstration. People have gone actually little more than that. That you can make a system of spins with a geometry of a star. By star, I mean one central object connected to various side branches, and the nitrogen vacancy is the central object, and these are all the neighbors. They are all interacting with the central nitrogen vacancy, but they don't have any interaction with each other. And there is not too many things you can do with the star geometry, but you can again ask for creation of some entangled states, which are non-trivial because now we have multiple candidates and you can do something about it, and it goes a little bit beyond this one spin memory. But so this demonstrates. And once people realize that these kind of systems are interesting, they've tried a different combination. Why only stick with diamond and carbon and nitrogen? I will play around with different atoms and different lattices and figure out if some combinations are useful or not. Well, they tried lots of things. Most of the things don't work, but there are a few which have useful properties, and people are still trying. And we don't know which one of them will end up being good for something or another. This nitrogen vacancy is already very useful for quantum sensing of various things, and people are trying to make actually devices which can be used in actual field practice, not just in the laboratory. So that is one step forward. Yeah.
This star geometry, the invisible is coupled to what, carbon-13?
Yeah, all several carbon-13 atoms neighboring to it.
When we say nitrogen vacancy in the center, so we have nitrogen at one lattice point and the electron at the other lattice point.
It's basically electron. Nitrogen doesn't play any role. It's an electron spin which is going to couple to everything else. All the other electrons are all paired up in chemical bonds, so they don't contribute. This extra electron which contributes.
So the point is the only electron.
Yeah, so this is the central free electron which is sitting there. And one example which kind of useful is the silicon vacancy in diamond. Again, it's a different chemical structure, but one of the carbon atom has to be replaced by silicon, which is a different element, and then you can have isotopes belonging to it, which can do non-trivial things. The point of looking at silicon vacancy is it has a long coherence time, whatever it is. So people have thought about whether they can make anything interesting from that or not. Okay. But I want to point out something else which is related to sensing, but also something which people are trying to make into a practical device. So what this electron levels allow you to do is because they are getting pumped by these lasers, they are no longer restricted to the thermal distribution or anything like that in the usual NMR. You can do a complete population transfer from one state to another, and polarization getting to a high level like 90 degrees is not a problem, 90%. So what is the interesting feature about it? And this came from playing around with various tricks, that this polarization can be transferred to another important material, which is water. Water has a large dipole moment, and so if there is some polarization created, it will interact and it can be transferred. And they tried it and it worked. They could transfer it from you don't need just one vacancy, you have to do many such vacancies. So actually you deal with what are called nanodiamonds and then you centers inside that. So there are lots of them, and they will interact in some manner and polarize water. And for that you don't have to do anything complicated. Make this nanodiamonds highly excited with this laser thing and just keep it in water. And well, when you are done with it, you can even filter out the diamond from it without too much of a problem. It doesn't dissolve. But now what you have is a polarized water. And the question is, how long does that polarization last? Okay. And that is an important experimental number. That it can survive for of the order of 10 minutes, which is a very practical time scale for medical applications. So what people have been trying to do is take this polarized water and use it as a diagnostic element in MRI, magnetic resonance imaging. And all you have to do is drink it. No radioactivity, no other complication of any type. Just drink that polarized water. It will decay, but it will last for some time. And within those 10 minutes, if you can do an MRI experiment, you will pick up all the signal. Of course, that water has to circulate in your blood and go wherever the organ is which you want to image, etc. But it seems possible. Okay. So there is right now a big effort to make this into a system which can be put in these healthcare centers. And all you are doing is somehow taking advantage of these magnetic resonances and making sure that the resonance has a long enough lifetime. It can have lots of applications. Yeah.
In traditional MRI, polarization is achieved by the magnetic field in the center, right? So
Yeah.
in this case, is the hope that so whatever polarized water is being transferred, it gets absorbed everywhere,
Yeah.
then the needed polarization field is eliminated with PCR versus that.
Yeah, there's no guarantee that water, when you drink it, it will only go to one part of the body. That doesn't happen. It goes everywhere. But you are imaging one particular organ and you assume that some part of that water will reach there through circulation in blood or whatever else, and then you will be able to take a good image of that particular organ.
Again, we show that when it mixes with light, the polarization is not lost.
Well, that people have to try out all those experiments. So
Can't we get this polarized water into bloodstream directly?
that you can do also. Means if you drinking and absorption takes too long, you put it in intravenously, whatever it is. But these are the things which are going on, and maybe somebody will make something commercial out of it. Right? It's a challenge, but it's something which seems promising. Okay, so yeah, this is another connection with all this magnetic resonance stuff. And now I can go to a different system.
So when we talk of water, so the spin polarization is from the oxygen, right?
It's all together. The water has a large dipole moment. It's a bent molecule, whatever it is. So the next object of discussion is ion trap quantum computing. And first, I will give the physical properties which make it useful before going into algorithms and anything like that. And lots of things have to be satisfied, in particular, whatever quantum signals you want to process, they have to have sufficient long lifetime. Otherwise, the effect will come and disappear, and that will not be any practical application. So, what is the structure of these ion traps and what are the properties? That is the first questions, and this is a linear, you can call it a register of from 10 to 100 ions, which you can make in the laboratory. Of course, you have to keep them in place. So, if the ions are left by themselves, everything from outside, the air molecules will come and collide and it will knock everything off. So, you have to have high vacuum. Needed to cut down basically all kind of scattering. So ions will be there, but they will interact mostly with the electromagnetic field, okay, not with collisions of other neighboring objects, etc. You can get rid of it by this high vacuum environment. Okay. So that is the first step. But how do you make this register? And that is also an interesting story, in the sense that the naive idea which you think of actually doesn't work. And the reason for that is very simple. So, if you use only the static electrodynamics, you cannot create such a system, and the reason for that is quite straightforward, that you can write down the Maxwell's equations or equations of an electrodynamic field, and you learn that the important part of that equation is just a Laplacian operator. So if you have a static situation, it reduces to Laplacian acting on E or B or whatever it is equal to 0. Now this Laplace's equation tells you something important. It's the sum of all the second derivatives, and that is equal to 0, which means if one of the second derivatives is positive, something else has to be negative. Otherwise, the sum will never be 0. And a simple consequence in terms of geometry is that you construct any electrodynamic configuration, the base you can have is saddle point. Stable in one direction, unstable in another. And that field cannot trap anything because of unstable direction. So, and this simple statement is called Earnshaw's theorem. You cannot use electromagnetic static fields to trap charged objects. Very different from our classical mechanical experience where you can make a trap and thing will remain confined. It doesn't work. So what do you do to get around it? And the bypass is to have time-dependent fields. Okay. And there are various demonstrations of this, that is, you can take a what you call unstable dynamics, and if you then just apply a appropriate time-dependent perturbation on it, becomes stable. One of the things which people actually can demonstrate very easily is that something like this object pen, I can't keep it on my hand because it will tumble about it, but if I shake it in the right manner, then people are able to hold it in one place. And that is, well, pen is probably not that easy to object, but people do it with a bigger thing like a basketball or something like that. And you can take it on a finger and you shake it right and it doesn't fall. Because what you are doing is essentially allowing it to fall a little bit, but by the same time the support has shifted, and then it will compensate for that particular fall and it comes back into equilibrium. Of course, you have to tune the frequency that the frequency of this time-dependent field matches the rate of fall in the unstable direction, but it is possible. Okay. And this technique, there is a very simple equation which can be solved to high accuracy to demonstrate these properties precisely. It is essentially dynamics in a field with periodic perturbation. So you can take a second order time derivative with the dynamics of an object, but then the potential is not a constant, but something like cosine omega t. And then you ask for, are there any solutions of this which are stable in time, and you can find a standard description of this Matthew equation in many mathematical physics textbooks. And it's a well-known result. Okay. So this was implemented in this ion traps by Paul. Paul is the name of a scientist, and the object is called a Paul trap. Of course, to make this and see it actually working, it was a technological exercise, and he did it and he got a Nobel Prize for it. So what does it actually do? So it has a quadrupole field, basically two-dimensional. combined with oscillating fields, and this is designed in 2 dimensions. So the 3rd dimension is free. And what happens is that the ions line up in the 3rd direction just from Coulomb repulsion. That is how this resistor is produced. Okay. And of course, repulsion depends on how many neighbors are there for each ion, etc. So this resistor, the spacing is not uniform. Towards the end points, the spacing is larger, and in the middle of the resistor, they are closer together. So that happens, you can actually observe it, and it doesn't create any problem. The most important part is what is the magnitude of this spacing. Okay. And the people have been able to design these things so that it's some number of the order of microns, several microns. It just depends on the strengths of various fields, and the oscillation frequency here is in the radio frequency domain. So again, some megahertz values like the NMR experiments. And this value offers one advantage which was not there in NMR. The distance is much larger, not of the order of angstrom or something like that. That the ions can be individually addressed by laser pulses. Laser's wavelength, which is the size of how accurately you can focus it, that wavelength is significantly below this kind of a distance. So you can say that when I shine a laser, I am only hitting one particular ion and not everything else which is nearby. This is something which was not possible in NMR. When you hit it, it hits everything, because everything was close by. But here, this is a individual addressability which comes from the structure and the various parameters.
So, is there any chance of scattering of laser light from the ion to the other?
Of course, the laser is interacting with the ions. It will get absorbed, it will get emitted, all those things will happen, yes.
So it will digital whether ions chips.
Depending on the frequency. All the energy levels are quantized. Only if you have matching frequency, it will cause a transition. Otherwise, nothing will happen. It will act like a transparent medium if it is not matching with any of the frequencies. So now such a thing is possible. What are you going to do with that? And I have to now give a more explicit description of the components. And this is there is one more thing I can tell you, that this is for the registers of this kind of ions, but the same Paul trap and the same strategy is also used for another sets of important quantum applications, and one of them is atomic clock, which also worked on a trapped ion. In a same kind of scenario, it's a Paul trap which is used, and you use the frequencies of that particular ion as a standard for time. And another quantum scenario which has been analyzed quite a lot with the same traps is a Bose-Einstein condensate. That can also be done with the same trap. There you actually don't use ions, but you use lots of atoms. They can be trapped in a similar manner, and lots of things about Bose-Einstein condensate have also been studied with the same kind of machinery. Essentially, they are all based on Paul traps. So now let me get back to the quantum register. What we need is a long-lived states. You got rid of all kind of unwanted scattering because of the high vacuum, but that doesn't mean that the states have become absolutely stable. They have their own internal instabilities, particularly from the controlling field or from its own decays, which occur irrespective of whether it is in vacuum or not. And you have to find some states of some atoms which are long-lived. Okay? And here, well, people had to search for various ions, and the popular ones are these elements which belongs into second column of the periodic table. Barium, calcium, and strontium which have excited state lifetimes of the order of a second. Okay, ground state doesn't decay, you don't have to worry about it, but you need two levels. The excited state will decay, and you have to find combinations which are generally called metastable, whatever it is. Then another thing which is implemented, which is actually a matter of convenience. So you need to address each ion individually, which is possible with the spacing, but you don't move the laser around, you just move the whole trap around. The laser is a complicated setup, and it's not so easy to slide it around. The ion trap is in the middle, and you just slide it around back and forth. The So depending on the position of that trap, you will be able to address one ion here, and you move it, and then you can address other ion, and so on and so forth. It's a kind of technological simplification. Then you need a measurement. So So this measurement is again going to be what is called a population measurement. How many atoms are there in one particular level? And that is done by creating a fluorescence, in the sense that here is not an ensemble thing. Here one particular ion will have one atom, but instead of making an ensemble, you can make it repeat the photon fluorescence over and over again. Okay, in the sense that yes, the atom is, that one particular ion is in this particular state, then I shine some light which takes it to some other level outside the processing region, which is not a metastable state. It will go to excited states, and then it will fall back. And you keep on doing it repeatedly at a very fast rate, because excited states which you use here is very short-lived. And so ion will just keep on going back and forth, and in the process emitting light, and that light you observe as a fluorescence. And you can actually do this. You don't need a sophisticated photodetector. You can take it to a stage where you can see it with your own eyes. So many of these traps, I don't know whether something was demonstrated on the science day here in the physics lab or not, but it used to be something which was demonstrated. You can trap the number of what you call atoms, or some of them are charged, so it makes an ion, and you can see it with your eyes by shining laser light with a pulse frequency. You get excited, then it decays, the laser basically goes off by that time, and then you can see the light coming out for it. So this is an important feature that it is possible. And that makes detection much easier. You don't need a ensemble, you can just do it with individual ions. And well, whatever I will say, these numbers are quite good. So that how reliably you can make these things, it's quite good. Greater than 99%, you can actually try to add more .9 after that. People have been trying to do that as well, but both these processes are sufficiently good once you have put the whole system in a vacuum that you can initialize it, which means put all these atoms in a ground state of that register and make this measurement by shining laser pulses on it, and that is a very useful feature to have. And other thing which is important is the properties of the ions are universal. Once you select some chemical element, you know what its frequencies are and how it is going to behave. It's not that one ion in one location will have a different frequency than another ion in another location. It doesn't happen. It doesn't even have anything like the chemical shift because these are isolated ions. All it needs is interaction with the surrounding electromagnetic field. And that interaction is described by what is known as a Jaynes-Cummings Hamiltonian. And this is in the weak field approximation, which will implicitly assume so that there are only interactions involving single quanta, not multiple quanta at the same time. Okay. So what is this Hamiltonian? You will find it listed in many different textbooks. Some notation is needed. So there is the energy for a number of photons together with its own number operator, a dagger A. Then there is a energy description of the two levels of the ion, which is written in the same language as Zeeman splitting in a magnetic field with operator sigma z by 2. This I have used the Zeeman label even though it's not the magnetic field here, but it's two ionic states, something of the same category. And then there is an interaction. And the interaction has a frequency which is the splitting between these labels, and I will just give the label for this, and it comes with two Hermitian conjugate terms which are written in terms of creation and annihilation operator for both photons and the two level systems. So a photon can get absorbed and the quantum two level system can get excited, which is a sigma plus, and the conjugate, the photon can get created by the excited state decaying to the ground state. So this is a very simple minded Hamiltonian known as a Jaynes-Cumming Hamiltonian, and the whole dynamics of the system is described in this language. The weak field approximation just means that I don't talk about double excitations. I just talk about one excitation at a time. Okay. That puts some, so limit on how strong a field I can have. If I have a strong field, there can be multiple excitations at the same time. I don't go into that region, and it will slow down the transition operation time. It's proportional to the strength of the field directly, or rather the product of the field and the time together. Hamiltonian times t is the exponent for evolution. So the question is it possible to still make this time small enough so that I can perform multiple operations within the 1 second lifetime which I have and avoid all the double transition? The answer is yes. You can have this thing, the transition operation time, still of the order of millisecond or smaller. It's not as fast as the radio frequency times in NMR, which are in microseconds. It's a little bit slower than that, but still there is enough gap between this operation time and the lifetime of the states. Okay. So this is a kind of structure. And yeah, one more thing I want to add over here, that this is, I wrote it for the photons, and I will need essentially the same holds for another interactions which the ions have. With another field which is not the photon, but phonon, vibrational modes. and the vibrational modes enter in this register because the ions are lined up, but they can still oscillate uh, in space. They have a Coulomb repulsion, but that does not prevent them from vibrating. Of course, the vibration levels will also be quantized and there will be some energy gap for it. And that is now something which you can work out from electrodynamics, that if I have two ions at particular separation and what is the force between them, and if it is a register, and I can find out what are the kind of frequencies which appear, and what is needed is a requirement which is something which I have not mentioned so far. So the ground state operation needs that the thermal energy is much smaller than the vibrational quantum energy. The vibration energy is of course much smaller than the electronic level spacing. So that is a generic feature. But I should not be able to excite these vibrational modes by the thermal environment of the trap. Whatever, I have put it in vacuum already, but I also need low enough temperature. And then this system will have kind of desired properties, and that is something which I will now describe next time. But it was a clever proposal made by Chirac and Zoller, and it was implemented roughly at the same time when NMR processing was also being demonstrated. Okay. So with all this physical structure and stability criterion and parameters in a specific range, now what do we need? And one thing is quite straightforward, that I need 1 qubit operations, but that is only some transition between ground state and excited state, and I can control it by just shining a laser on a particular ion. Frequencies are different, but the principle is not any different than any other electromagnetic field situation. So this is something which can be implemented without too much trouble. Of course, I don't want to continuously keep on moving the lasers around to generate various rotation axes, so I use Euler angle decomposition so that those axis remains fixed. But it can be done without too much trouble. The more important part is, where do I get the 2 qubit interaction? Okay. And because the Coulomb repulsion is not going to give me a 2 qubit interaction, I need interaction which depend on which of the states of every ion has, its ground state or excited state, charge is not going to change. So the Coulomb repulsion cannot play any part in it. And that was the novel contribution by Sirac and Zoller. And what they showed that the ions in the trap have vibrational modes, and the lowest one of that is the center of mass mode. And the property of the center of mass mode is that the whole thing moves in coherence. And what they showed was that you can create a situation where the movement of the center of mass in the trap will be able to transfer the quantum signal from one ion to another. There is an advantage inside here is that you can transfer the signal from any ion to any other ion, because in center of mass all of them are coupled together. Distance doesn't matter. So whether it is next to nearest ions or whether it's far away, everything is just going to move together, and that so the this is an advantage compared to the kind of situation which was there in NMR, where interaction was only nearest neighbor. Here it is not so, it can be between any two ions, and the distance does not play any role in the execution. But how this transfer actually takes place, it's something I will describe in the next class. It's basically shining light on one ion, waiting for a particular time, and then shining light on another ion. And if you adjust the time pulses correctly, the state will go from one location to another. You can implement control naught or control Z or any one of those gates by that kind of strategy.